Asteroids are the geologic remnants from the dawn of the solar system. We want to understand, how did Earth become a habitable planet? How were the seeds of life delivered to Earth that trigger the origin of life and evolution as we know it?
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Asgas.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
Com.
Go.
Timer.
Go.
GCQ.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
AC is go.
Range coordinator.
Clear to proceed.
Launch director.
LD is go, and you have permission to launch.
Proceeding with the count.
10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Fire rates look good. Starting pump speeds and check pressures are within 10. Main chamber pressures have plateaued, begun to ramp off.
During the voice of Marty Malinowski, the Atlas has begun a pitch and yaw maneuver to steer to its planned path, 28.5 degrees inclination from the equator.
As our main chamber pressure is almost plateaued at this point. Marty 180, check pressures are good.
45 seconds into flight.
Program is complete. Boosters throttled down.
And the Atlas rocket carrying OSIRIS-REx has gone supersonic. Standing by to pass through max Q, maximum aerodynamic pressure.
Max Q, vehicle migrates continue to look good.
This is the point when the mechanical stress on the rocket reaches its peak
And
because of the
have
rocket's
throttle back
velocity
up.
and resistance created by the Earth's atmosphere.
And
And
we
you see the
have
solid rocket booster jettison.
separation looks good.
So for our survival, it's essential that we understand what's out there in our environment in space. And this is one of the main objectives of the OSIRIS-REx mission. We'd like to go out and meet Bennu before something like Bennu comes and meets all of us.
We're 1 year in outer space, and we are targeting an Earth gravity assist on September 22nd. The spacecraft will pass about 17,000 kilometers over the surface of the Earth, somewhere over Antarctica.
It's free energy, basically. We can achieve this inclination change without having to expend any of our own fuel.
We needed an object whose orbit was pretty similar to the Earth, so that we could launch off of our planet, rendezvous and spend some time at the asteroid, and then leave and bring this precious scientific cargo back to Earth.
Bennu is what's called a NEO, a near-Earth asteroid. So instead of orbiting in the main asteroid belt between Mars and Jupiter, it has an orbit fairly similar to our own planet, Earth.
Bennu is currently a near-Earth asteroid, but it's a recent wanderer into the inner solar system. We actually think it's fragments of a much larger asteroid that was catastrophically disrupted maybe 1 billion years ago. We learned literally about 1 week after getting into orbit that Bennu is what we call an active asteroid. It is ejecting particles from its surface. These particles are coming off at relatively low velocities for the most part. They're actually going into orbit, spiraling around the asteroid, providing some excellent science, allowing us to map out the gravity field of this small body at an unprecedented detail, way beyond what we expected to do.
As challenging as it is actually getting to Bennu, capturing a sample of the asteroid is something else entirely. And the team needed to develop this remarkable system. The OSIRIS-REx mission has been in development for almost 20 years, with the engineers and scientists developing new technologies and strategies to accomplish something that's honestly never been done before. And this is particularly challenging because Bennu has such a weak gravity field. So when you think about going into orbit around something, how do you orbit something where the gravity can't grab you and actually push you into orbit? It's all about flying the spacecraft. It's also very difficult to take a sample in a very low gravity environment.
We did expect this asteroid to look sandy and beach-like, and that was based on the thermal properties as determined from telescopic observations from Earth. And we got there and we used the OTIS and our OVIR spectrometer to map and produce a thermal inertia characterization of the entire surface. And everything turned itself upside down based on our models. The areas that we thought would be beach-like based on thermal properties turned out to be the largest boulders on the asteroid's surface. And the more fine-grained regions turned out to have what we call this higher thermal inertia, completely opposite of everything we expected. We spent an enormous amount of effort selecting the area on this asteroid surface where we wanted to get the sample from. And this was a real challenge because the original guidance accuracy was 25-meter radius, and we're trying to get into an area that's 10% of that size. We have solved that problem with our amazing natural feature tracking solution.
OSIRIS-REx is all about sample return, and we picked Bennu for a very special reason. We believed from our astronomical telescopic data that it was rich in carbon, primarily in the form of organic molecules, and that it contained abundant water locked up inside minerals called clays. So for me, the most exciting results were when we got the spectrometer data down, and first we saw that clear signature of water all over the surface of Bennu. It's a very wet, hydrated rock. And then a little later on in the mission, we got the signal that there was abundant carbon, and it was everywhere on the surface. We picked a great sample site, Nightingale, which we think is going to give us wide representation of the different rock types on the asteroid. So everything I hope that this mission would deliver in terms of the sample, Bennu has given us.
Once we fire the thrusters for the checkpoint maneuver, we're actually going to start descending down towards the asteroid surface.
And we are bringing you live coverage of our attempt to collect a sample from the asteroid Bennu.
OSIRIS has begun moving the solar arrays to the Y-wing configuration to avoid possible contact with the surface during tag.
The spacecraft has deployed its robotic TAG-SAM sampling arm, so the arm is ready, in position to collect that sample.
This is it. You know, the engines have given us a push in the right direction, and OSIRIS-REx is on course to make touchdown on an asteroid.
Attitude control system has transitioned to touch-and-go mode. OSIRIS has descended below the 5-meter mark. The hazard map is go for tag. Tag expected in 50 seconds.
We're going in. We're going in.
Touchdown declared. Sampling is in progress. Sample collection is complete, and the back-away burn has executed.
All right. We're on our way back. The back-away thruster is fired, so we're safely moving away from the asteroid surface.
And the surface responded almost like a fluid. I like to compare it to one of those ball pits at a kid's playground. So we learned that the surfaces of these rubble pile asteroids are very loosely consolidated.
So what you're seeing is the spacecraft descending at a leisurely 10 centimeters per second to the surface, 15 times slower than walking speed. It contacts, the spacecraft senses contact and fires the gas. The gas mobilizes material underneath the TAG-SAM head. That gas escapes into the vacuum of space through the perimeter, and materials collected inside the TAG-SAM head. The spacecraft fires its thrusters and backs safely away from the surface of the asteroid.
We have overcome the amazing challenges that this asteroid has thrown at us, and the spacecraft appears to have operated flawlessly. We made it down to the asteroid surface. We were in contact. The gas bottles fired. We backed away successfully from the asteroid surface, and we have some work to do to determine how much sample that we have collected. After we're well away from the asteroid and everything has kind of settled down, we have that robotic arm. We're actually going to use that to put the TAG-SAM head into the field of view of SAMCAM.
And if everything has gone right tonight, a little bit of Bennu will be coming back to Earth in 2023.
After 2.5 years of space operations near Asteroid Bennu, NASA's first asteroid return mission, OSIRIS-REx, is ready to bid farewell to this fascinating rocky object.
All stations, navigation has received confirmation of settle and burn start.
So that was the confirmation of OSIRIS-REx's engine burn start.
We have a nominal ADM burn, and we're bringing the samples home.
Following the maneuver today, the spacecraft will be moving rapidly away from Bennu, but it will still take almost 2 years or 2 full orbits about the Sun for OSIRIS-REx to catch up with the Earth.
We've got those samples in hand and it's time to bring them back. So I'm really excited for this next phase and to see what the scientists learn once they have these samples in hand here back on Earth.
We think we actually might be coming back with a baby picture of what the solar system was like, of what our chemistry was like billions of years ago. We're looking for our own origins out there, and that's why we've gone so far to bring a bit of Bennu back.
The part that excites me the most is that 75% of the sample we bring back is archived for future generations. So scientists, perhaps not even born yet, will use techniques we can't imagine to ask questions we don't know how to phrase yet. And so this is a decades-long legacy that OSIRIS-REx brings to science to study.
It's been fantastic to watch the OSIRIS-REx mission so far, and I'm really, really excited for what's ahead tonight, and I want to say congratulations to the entire team.